Okay, so good evening, all of you. Last time we did some recap of sequences and we have tried solving some few problems. This time, in today's session, also we'll continue solving some more few problems and then we will recap the another topic from real analysis, that is infinite series of real numbers. This was a problem which I left last time. I hope all of you have tried and you must have got the answer. Let us do a quick, easy problem. Am I audible to all of you?
Yes,
Okay. Is the problem visible?
yes,
Yeah. So other students are also joining. Meanwhile, those who are joined can try this problem. Yeah. So I will evaluate this limit. You can easily see this is you multiply by n inside, so you'll have something like this. Then what will you do with the second term?
Sine 1 by 4n divided by 1 by n.
Yeah. So you take this n in the denominator of sine 1 by 4n and then you adjust the angle and then you split the limit. Yeah, very good. What is the answer of second limit?
It's 1 by 4.
Yeah, this is 1 and the answer is 1. What about the first part of the limit?
It's a infinite by infinite form and will be solved by L'Hopital's rule.
Okay, so what about this first term?
This is
N is here also, the
bounded.
angle of cos. Yeah. So you
Oscillating
observe this is
between -1
this
and
is bounded.
bounded. And then you apply limit to this. So this, as you have correctly guessed, is infinity by infinity form. So we can apply L'Hopital rule. And this will be equal to derivative of numerator upon derivative of denominator. So that will go to 0. So I hope the final answer is 1 by 4. Yeah, all of you got this?
Yes, sir.
Okay, good. So with this quick, easy problem, let us see another set of problems to get asked in the exam. This the first we want to find. You want to put the value. So if you observe carefully, there are two parts actually. Let me try computing. Let me put this limit in two parts. Let us focus first.
Sir, you are not audible.
Yeah. Audible now? Is it is my voice? Is it okay? Yeah. Is my screen visible?
Yes, sir.
Okay. Okay. Let us focus on first part of the limit. There's something in the numerator and there is something in the denominator. Have you seen such kind of limit?
Yes, sir.
Okay. Okay. So how will one go about this?
With the limit of some formula.
Okay. Okay. So you may feel that possibly like this 1 by n raised to 5 into, can write this as summation k from 1 to n k raised to 4. Yeah. Is it is it fine?
Yes, sir.
Numerator you can write in compact sum notation. So it will
Yes,
be
sir.
like this. Okay. So whenever see the examples of limit we have solved in last lecture also previous to this, several examples we have seen. Sometimes it is easily solvable, but this time looks like when I try applying limit n tends to infinity, this finite sum will become infinite sum, turns in infinite sum. So we need to add infinitely many numbers at the numerator, and the denominator is also going towards infinity. So whenever you see this kind of situation, you have to think on something called as Riemann integration. I hope you all must have gone through Riemann integration of one variable calculus. F from closed interval ab to r is bounded function. And then there's a big definition. What do we mean by f is r integrable or Riemann integrable on closed interval a comma b? There are several concepts involved in this. For example, you have to take Cartesian closed interval a comma b, and then you have to compute upper Riemann sum, lower Riemann sum, then refine the partition. Again compute upper Riemann sum, again compute lower Riemann sum. Continue this process for refining partition more and more, number of subintervals. Finally, you compute something like UF and LF. UF is infimum of all upper sums, where P is partition of closed interval A comma P, and LF is supremum of all lower sums, where P is partition of closed interval A comma B. And we say function is Riemann integrable if this upper Riemann sum matches with lower Riemann sum. There are some obvious relations like upper Riemann sum is greater than equal to lower Riemann sum, and this upper integral is greater than equal to lower integral. So f is Riemann integrable if upper integral matches with lower integral. So this limit looks like totally possibly with Riemann integration, but yes, there is a connection. So I can write this limit as this way. Limit n tends to infinity of 1 by n into, you keep just 1 by n outside and rest of the powers of n inside. We'll have something like this. A by n raised to 4. K runs from 1 to n. Is it okay up to here? You just pull out one power of n outside and rest of the things you write in compact sum notation. So it will like this. So whenever you
Yes,
see this kind of term appearing in limit, whenever you see this kind of term appearing in limit, it's a sign that to evaluate this limit, we may need to use concept of Riemann integration in the following way. So using this observation, I can define a function. Consider a function f of x is equal to x on closed interval 0 comma 1. And you try checking whether this function is Riemann integrable on 0 1. It is obviously Riemann integral because the function is continuous. And we have seen one result in Riemann integration. Every continuous function is Riemann integrable. Okay, so function is Riemann integrable. That background we already have. But if I want to evaluate its integration by using definition, then I need to go through all these things. So a suitable partition I need to choose. So we must have seen this is a suitable partition. 0, 1 by n, 2 by n, 3 by n, and so on. N by n is equal to 1. This partitioning closed interval 0 comma 1 into n equal parts. Partitioning closed interval 0 comma 1 into n equal parts. So your ith subinterval is xi minus 1 comma xi. That's nothing but I minus 1 comma n comma I by n. That's ith subinterval. Then you need, so what I'm trying to do is I'm trying to construct upper Riemann sum for this function on this interval with respect to this partition. Is it okay? So by definition, upper Riemann sum is summation k from 1 to n, or mk into k minus xk minus 1. That's a length of ith subinterval. And where, what is mk? Mk is supremum of fx where x belongs to ith subinterval xk minus 1 comma x. Okay, so let's compute mk here. So mk is supremum of fx, that is x, where x belongs to I minus 1 by n comma I by n. So what is the supremum? What is my function? X itself, the identity function. So supremum will be right extreme. Yes, correct. Supremum will be at right extreme. Okay, let me k minus 1 by n comma k by n. So supremum is k by n. And what is the length of the partition? Length of the kth subinterval? 1 by n. That's very good. So what is the upper Riemann sum? Let us plug in. Summation k from 1 to n. Mk is nothing but k by n into length of the interval 1 by n. So is this upper sum looks like limit of the thing that we want to compute? Yeah, or is there any variation? This is the limit that we are interested in computing. By considering an identity function on 0, 1 and by taking this partition, we have arrived formula for the upper sum looks like this. There is slight deviation. What is the deviation? We have got 1 by n here also. And yeah, 1 by n here also. We have got k by n here also. We have got k by n here also. But here we have k by n raised to 4. So what modification is required to get this k by n raised to 4? Here. Yes. Here also k by n, here also k by n. But here we have k by n raised to 4. Here we do not have raised to 4. So which function do I need to choose?
X raised to 4.
X raised to 4. Is it okay for all of you? Did you follow this? If I choose x raised to 4, then what you will get? Can you do the calculation? Supremum of x raised to 4. So that will be again x raised to 4. F of x is equal to x raised to 4. The derivative is f dash of x 4x cubed, that is greater than 0. Greater than equal to 0 on close interval 0 comma 1. Okay. So there's a function whose derivative is greater than equal to 0. So what can I say about such function? If
Strictly increase.
yeah, function is increasing, so its supremum will be at the right endpoint. So supremum will be k by n raised to 4. Yes. Now if I take this function, then I get UPF something looking like this. That is 1 by n summation k from 1 to n a by n raised to 4, which is exactly equal to this limit. Did you see that? Yeah.
Yes.
Yes. Now I want its limit. So limit n tends to infinity of 1 by n summation k from 1 to n a by n raised to 4. That will be equal to limit n tends to infinity of UPN of f, upper sum of the function f with respect to partition p suffix n, where p suffix n is this specific partition. So if I take limit n tends to infinity, what will happen to this partition? the number of subintervals will go on increasing. Yeah. And the length of each subinterval will go on decreasing. That means we are refining the partition. So in short, we want, when you compute limit of this upper sum, we are computing upper Riemann integral. So this limit will be exactly equal to upper Riemann integral. But upper Riemann integral will be equal to lower Riemann integral. Why? Because we know it's a simple polynomial function which is continuous. And every continuous function is Riemann integrable, as f is R integrable. Is it okay? Yeah.
Yes.
And we know how to compute simply this, that is integral 0 to 1 x raised to 4 dx. The answer is x raised to 5 by 5 integral 0 to 1, that's 1 by 5. Is it okay?
Yes, sir.
Yes,
Yeah?
sir.
Yes, sir.
Yes. Yes, very good. So we got first part of the limit evaluated. But there is another part also. Let's focus on that. Now we want this. Limit n tends to infinity 1 by root 10. 1 by root 10 plus 1. 1 by root 10 plus 2 plus and so on 1 by root of 4n. So again we observe is equal to 1 by root 10 into summation a from 1 to n, 1 by root of n plus k, or summation k from 1 to 3n, not just n, it's summation k running from 1 to 3n, 1 by root of n plus k. Okay, so this is again, is it possible to bring this in this kind of form? Something looks like k by n. Yes, we can pull out root n. So if I pull out root n, what will I get? By root of 1 plus k by n, and the root n is outside. Is it okay? And this root n you can actually bring out of the sum, and you'll have something like 1 by n summation k from 1 to 3n, 1 by root of 1 plus k by n. And we want limit of this. Here everywhere we have limit n tends to this term. This term looks like this. Is it okay? So this limit will be equal to limit n tends to infinity 1 by n summation k from 1 to 3n, 1 by 1 plus k by n. Is it okay up to here?
Yes, sir.
Yes, very good. Now, can you identify or can you apply the same trick that we have applied here? You've identified some function and some closed interval, and then we computed its Riemann integral by using definition by considering a partition like this. Same thing is applicable here also, because we got something in the form of k by n. So that suggests this limit can also be evaluated by using Riemann integration. So we need to identify a function. So it's easy. You replace k by n by x. You replace this by x and write the expression. So what is that?
1 upon root of 1 plus x.
Yes, very good. On. I need to identify the interval also. What should be the interval?
0 to
There's a
3.
difference. Yeah, yes, very good. Here the interval was 0 to 1. Here the interval, because the sum was running from 1 to n. But here the sum is running from 1 to 3n. So that suggests the interval we should choose is 0 to 3. And the same partition will work, Pn. But Pn is this time not just up to here. We need partition this further. So 1 plus 1 by n, 1 plus 2 by n, and so on. We'll have 2, then 2 plus 1 by n. So length of the subinterval, we are keeping it as same 1 by n. Is it okay? Length of the subinterval, we are partitioning this interval 0, 3 into equal parts with length of the each. So this partition we are considering. And then you apply possibly instead of upper Riemann sum, this time lower Riemann sum. Because what is my f of x? 1 by root of 1 plus x. What will I get f dash of x as? Minus 1 upon 1 plus x into 1, 0 plus 1. Yeah. So this is less than 0 on closed interval 0, 3. Because x is positive. So minus of that becomes negative. Here f is decreasing. F is decreasing. So instead of upper Riemann sum, we are computing lower Riemann sum. What's the definition? Summation k from 1 to 3n, because there are 3n parts, small mk into length of each subinterval, that's we have agreed to kept as 1 by n. Where what is mk? Mk is infimum of f of x. F of x is 1 upon 1 plus root x, where x belongs to k minus 1 by n, comma k by n. So this time function is decreasing. So its infimum will be at right or left endpoint.
Right.
Right endpoint. Yeah. Function is like this, in decreasing kind of function. And on this interval, we are observing the infimum. So infimum at the right endpoint. Here it's a infimum, and that is at the right endpoint. Very good. So this is 1 by root of 1 plus k by n. And then you plug in the definition of LPF. We have k from 1 to n, 1 by n, 1 by square root of 1 plus k by n. That is exactly equal to the limit that we want to evaluate. 1 by n summation k from 1 to 3n. So limit of this, limit n tends to infinity of 1 by n, summation k from 1 to 3n, 1 by root of 1 plus k by n, that will be equal to integral 0 to 3 f of x, root of 1 plus x dx. Evaluate this and tell me what is the answer.
Two.
Yeah. 2. So you can complete the solution. So my final answer will be addition of this and addition of this. That will be the final answer of this limit. Is that okay? Let us move on to, is it okay? Can we move on to next question? Those who have finished can go for this sum. I hope it's easy now to go further. Okay, some of you got 4, some of you got 2, some of you got 11 by 5, some of you got 2.2, some of you got 21.5. What you will get? This will be equal to integral 0 to 0, 1 plus x raised to minus half dx. So 1 plus x raised to minus half plus 1, that is half. 1 half, 0 to 3. 2 times 3 plus 1, 4 raised to 1 by 2. Minus 1 raised to 1 by 2. So that's equal to 4. Or not 4. 2 into 2 minus 1. That's 2. Answer is 2. So final answer is 2 plus 1 by 5. 11 by 5. Let's move on to this question. Is it visible to all of you? There are two sequences of real numbers which are defined by this way. A1 is equal to 1. An plus 1 is defined like this. And Bn is defined by using terms of An. Then we want to conclude something about An and something about Bn. So it's a temptation. Let us figure out what is An. What is A1? A1 is 1. What is A2? A2 is A1 plus minus 1 raised to 1, 2 raised to minus 1. Is that okay? That is 1 minus 1 by 2. That's A2. A3 is A2 plus minus 1 raised to 2, 2 raised to minus 2. So that will be A2 we have already computed here. Let's plug in the value of A2. 1 minus half plus 1 by 2 square. Is it okay? Can you compute A4 now? Compute A4. Tell me कितना आएगा? So if you have computed, it will be like this. 1 minus half plus 1 by 2 square minus 1 by 2 cube. So this shows some pattern. An plus 1 will be 1 minus half plus 1 by 2 square minus 1 by 2 cube and so on. Plus minus 1 raised to n into 1 by 2 raised to n. Is that okay? What kind of progression is this? Do we have any compact formula for this? Is this a geometric progression?
Yes, sir.
What is the common ratio? Common ratio is
-1/2.
yes, and yeah, correct. -1/2.
1/2.
And the absolute value of common ratio is less than 1. So we know where does this converges? 1 upon 1 minus a. The first term is 1. Sorry, 1 upon 1 minus r. That is 1 upon 1 minus of half. 1 upon 1 plus half. That is 2 by 3. an plus 1, we got something about an plus 1. An plus 1 go to 2 by 3. So where does an will go?
2 by
An will
3.
also go to, yes, an will also go to 2 by 3. Okay, so we got information about an. What about bn? Let us figure out what is bn. Bn is 2 times an plus 1 minus an by an. That is 2 times an plus 1 by an minus 1. I can write it like this. We divide by an. Is it possible to compute limit of bn? Go to
Yes.
limit. Yes. What you will get? Limit of an is 2 by 3. Limit of an is also an plus 1 is 2 by 3 and limit of an is also 2 by 3. So the quotient will go towards 1. So answer is 1. Is that okay?
Yes, sir.
Yes. Good. So which option is correct then? First option says an converges to 0. That's not correct. An converges to non-zero real number and bn is Cauchy. An converges to 0. That's not correct. An converges to non-zero and bn is not convergent. But we got bn is convergent. So correct option is an converges to non-zero and bn is Cauchy, because we know that relationship between convergent sequence and Cauchy sequences is that every Cauchy sequence is convergent. Yeah. I hope it is clear to all of you.
Yes, sir.
We go on to next question. This. If an is summation k from 1 to n by n square plus k, then the sequence an, bounded but not convergent, converges to 1, converges to pi by 4, not bounded. So it is tempting to write this an as pull out n from the denominator. Then it will look like n into n plus k by n. But this n get cancelled. Then I'll have something like k from 1 by n plus k by n. So it is tempting to think of Riemann integration, but every time it may not work. So you can give a try figuring out some function and some partition. Possibly you may be able to write this an as either upper Riemann sum or lower Riemann sum, or possibly Riemann sum with respect to some tact partition. But instead of doing it like that, let us expand the sum. K from 1 to n by n square plus k. k is equal to 1, it is n by n square plus 1, n by n square plus n by n square plus 3, and so on. N by n square plus n. This is how it looks like. Okay. Sometimes answer maybe we can get by comparing terms to each other. For example, here if you observe the numerator is same, that is n n n everywhere. The denominator keeps on changing. And there are two terms in the denominator, n square plus 1 on the left extreme and n square plus n on the right extreme. And there is in between you have all terms like this, n square plus k. So what kind of relation I can have between these three terms for k varying between 1 to n? Look at the left extreme, that is n square plus n. N is fixed. We are not varying n. We are just, for fixed n, we have written an. So there are n terms in the expansion of an, addition of n terms. And this contains several denominators. We have
Less,
observed
less than equal.
less than equal. So this is less than equal to this, and this is also less than equal to this. Because the varying quantity is only k. Varying quantity is k. Rest of the things are unchanged. They are constant. Okay. So I am trying to manufacture this term by using this relationship. So I got a relationship with a simple observation, n square plus 1 less than equal to n square plus k less than equal to n square plus n for all k. So you take reciprocal. N square plus 1, n square plus k, 1 by n square plus n. After taking reciprocal, we are aware that inequality become reversed. Inequality become reversed. And then there is n in the numerator. So you multiply by n throughout. You have n by n square plus 1 greater than equal to n by n square plus k greater than equal to n by n square plus n. Is it okay? If I multiply by positive constant, inequality remain same. So we are using several properties of inequality. We get something like this. Now an is actually addition of the middle term as k varies from 1 to n. So let's manufacture an. So you need to take addition. You have to add all this n inequalities. So this is true for all 1 less than equal to k less than equal to n. So you take addition over k. Summation k from 1 to n, n by n square plus 1 greater than equal to summation k from 1 to n, n by n square plus k greater than equal to summation k from 2 n, n by n square plus n. What will happen to this extreme left? N by n square plus 1 is constant with respect to k, so it will come out. And what will be there in the inside? Only 1. Middle term is an. And the right extreme is also the same thing, n by n square plus n into summation k from 1 to n, 1. So it's obvious that summation k from 1 to n, you add 1 n number of times, you'll get answer n. So this is n square by n square plus 1 greater than equal to an greater than equal to n square by n square plus n. Okay, good. How does it help? We want limit of an. Then the sequence an, we want to conclude about convergence of sequence an. We are trying to find limit of sequence an. So does this help, this inequality, to get the limit?
Quiz theorem.
Yes,
Yes, sir.
Quiz theorem. Yeah. So it is observation. Both the extreme sequences goes to 1. So by squeeze theorem. An is convergent and converges to 1. So we got a correct option. What is that correct option? B. Is it okay? Observe this. So sometimes inequalities you need to observe and then we can get the answer. One similar kind of question. You all please try this. Is it visible to all of you? It's almost a similar kind of question, but here the numerator was constant n. Here the numerator is also changing. 1, 2 square, 3 square, and so on n square. So try computing this. Yeah, anybody?
1/3.
1 by 3. Yes. Very good. Answer is 1 by 3. The similar kind of trick you have to apply, like comparing terms, finding a suitable bound on left and suitable bound on right, and then finally using squeeze theorem. Use squeeze theorem. Okay, you can give a try. Is my screen visible to all of you?
Yes, sir.
Yeah. Try this. What you will like to apply here? So this limit n tends to infinity, pi by n into summation k from 1 to n sine of pi by 2 plus pi by 2 into k by n. So there's already a term involved in the form of k by n. And there's already 1 by n here. It suggests choose f of x as sine of pi by 2 plus pi by 2 into x on close interval 0 comma 1. And then you try writing the Riemann sum. We take the same partition Pn as 0, 1 by n, 2 by n, and so on. 1 by n, that's nothing but 1. And you choose x k star belonging to k minus 1 by n, comma k by n. You choose these points. Xk star is equal to 1 by n, sorry, k by n, belonging to this interval. So we are, from the first subinterval, we are choosing 1 by n. From the second subinterval, we are choosing 2 by n, and so on. So when you start with a partition and with already some pre-chosen points, such a partition is called as stacked partition. Tagged partition. Is that okay? So you compute Riemann sum of this function with respect to the stacked partition. So we are not computing something like lower Riemann sum or upper Riemann sum, but we are computing Riemann sum of f with respect to the stacked partition. It's summation f of xk star into length of the subinterval k runs from 1 to n. Summation k from 1 to n. That will be sine pi by 2 plus phi pi by 2x pi by 2 into k by n to 1 by n. That is exactly equal to this limit. Is that okay? In this case, why we have chosen stacked partition is that sine function keeps on oscillating like this. So computing supremum, infimum may be problematic. We may not get the exact limit if we try to use the definition of upper Riemann sum or lower Riemann sum. Okay, so that's why we have choose stacked partition. So in stacked partition, we have freedom to choose the points as we want. We evaluate f at that point. We multiply value of f with respect to the length of the subinterval and you add all these products. If f is Riemann integrable, then limit of this will go to integral of f. This will be equal to integral 0 to 1 fx dx. Is f Riemann integrable? What is my f? Sine of pi by 2 plus phi pi by 2 times x on closed interval 0, 1. So is f Riemann integrable?
Yes, sir.
Yes, because f is continuous. So that's why Riemann integrable. So you can compute the integral and you can get the answer. Answer is, anybody got the answer? Check. 2 by 5.
2 by 5.
Yeah. Yes. I hope it is followed to all of you. Try this one. There's a sequence. You have beta belonging to open interval 0, 1. And we have a sequence 1 upon n, n beta. This represents a greatest integer, but less than or equal to x or not greater than x. Do you know where the sequence goes? What is the limit of this sequence? Where does it go as n tends to infinity?
Beta.
Yeah. Yes. Yeah, others, please think. Where does the sequence goes? We do say a statement in real analysis. For every real numbers, there exists a sequence of rationals converging to that real number. Real number. Do you know this statement?
Yes, sir.
This is also called, goes under the name of density of rationals. Rational numbers are dense in set of real numbers. So this is that sequence of rational numbers. First of all, is it a rational number? Beta is any real number between 0 and 1. So 0 less than beta less than 1. So n times beta will be some real number. How will you go on adding beta n times? That is what n times beta. So n times beta may cross 1. It will be somewhere between 3 and 4, or possibly maybe some random natural number, sorry, real number. Okay, which may not lie in the same interval between 0 and 1, where does beta lies. But nevertheless, n times beta is integer, because n times beta is a greatest integer, but not greater than n times beta. So that's an integer. And then you are dividing by n. So that belongs to set of rationals. Okay, so this is a rational number. Though beta is a real number, integer part of n beta upon n, that's a rational number. And it's not difficult to see this actually goes to beta. You just have to observe n times beta, integer part of n times beta, or the greatest integer less than or equal to n beta. Where does it lies? In between, it will, beta is a real number between 0 and 1. N times beta is a real number. As being a real number, it will lie between two integers, two consecutive integers. As being a real number, it will lie between two consecutive integers. Which are those two integers? The highest among them possibly n beta. And what is the integer previous to n beta? What is the integer previous to n beta? You subtract 1 from n beta minus 1. Do you agree with this? For example, if I take beta is equal to 0.5, then what is my n beta will look like? The sequence. How does the sequence will look like? What are the terms of the sequence? 0.5. Let me write. First of all, beta, 2 beta, 3 beta, and so on n beta. And the sequence continues. Beta is 0.5, 2 beta is 1, 3 beta is 1.5, 2, 2.5, 3, and so on. It continues like this. So n beta can be an integer. For example, if beta is 0.5, see, whenever n is even, n beta is integer. Is it okay?
Yes, sir.
Yes, very good. So n beta can be equal to, integer part of n beta can be equal to n beta. And then it will lie on the lower side, you'll have n beta minus 1. So integer part of n beta will lie in between n beta minus 1 and n beta. Now you need to divide by n. So you divide by n. N beta minus 1 by n less than equal to integer part of n beta upon n less than equal to n beta upon n. What you get after on the extreme left, you get beta minus 1 by n less than equal to integer part of n beta on n. On the extreme right, you get beta. So on the extreme right, we got a constant sequence beta. Where will it go? It will go to beta. On the extreme left, we have some sequence beta minus 1 by n, beta minus 1 by as it goes as n tends to infinity. It also goes to beta.
Beta.
Yes. So by squeeze theorem, what I can say, integer part of n beta by n, this goes to beta as n tends to infinity. Okay. So this is a required sequence of rational numbers converging to given real number beta. Okay. But my sequence here in the problem is plus something else, one more term, n square into beta raised to n. N square into beta raised to n. So this I have observed, this goes to beta. What about the second part of the sequence? Where does it goes? So n square beta raised to n. Beta is in between 0 and 1. So its nth power will go to 0. And the coefficient n square is going towards infinity. Is it okay? So this is 0 into infinity form. So you convert this into infinity by infinity form. One upon beta raised to minus n. Is it okay? Sorry, I made a mistake.
Yes, sir.
Beta, yeah, beta raised to n, that is beta raised to minus n. And then you apply L'Hopital, infinity by infinity form. So by L'Hopital, limit of this derivative of numerator upon derivative of denominator is minus n, beta raised to minus n minus 1. Sorry. Beta raised to minus n का derivative.
Beta raised to minus n log beta.
Yeah, beta raised to minus n into log of. And you again apply one more time L'Hopital and you can observe numerator n will vanish and you have n in the
Sir,
denominator.
isn't it 2n upon beta to the power minus n log 1 by beta?
Yeah, beta raised to minus n. Yes, log of beta raised to minus 1, correct. Then you apply more times 2 upon beta raised to minus n into log of beta raised to minus 1 square. And this will clearly goes to 0. Is it okay?
Yes, sir.
Yeah. You can also observe like this. This term is n square upon beta raised to minus n. Or this. this term is going towards infinity and this term is going towards 0. But beta raised to n go towards 0 faster than n square going towards infinity. So the product will go to 0. That way also you can observe.
Sir, I have a question.
Yes.
Sir, is there any sequence of, as you said, it is going faster, beta to the power n is going faster than the n square, going to the infinity. Is there any sequence to know this is short trick or anything like that?
Is that any sequence which?
Which function is going faster to infinity? As x tends to infinity, which function is going to faster to infinity, which is slower than this, like that?
Means possibly
Maybe x to the
1
power
upon
n.
n
Yeah.
square and say some 3 raised to n, something like that.
Like that of functions, right?
Yeah. So this is going towards infinity. This is going towards 0. But 3 raised to n go towards infinity faster than 1 by n square going towards 0. Because 3 raised to n is a kind of exponential power, exponential kind of thing. So this will increase faster. You can check. You can apply L'Hopital rule twice and you'll get the product goes towards infinity.
Thank you, sir.
Yeah. Okay. This problem looks like problem of computing limit, but it's not actually. It is problem of computing limit, but may not be limit of a sequence. It is limit of something else. Let's try to understand this. What is this? Limit n tends to infinity. F of 1 by n. There is something at the end, you have k times f of 0. That means I can split this f of 0 in k terms. And how many terms are this? How many they are in number? K terms. So there are k terms and here you have coefficient as k. So this suggests you split f of 0 to every term. Will it match? Yes,
Yes,
it will
sir.
match. There are exactly k terms in the addition and f of 0 is also appearing k times. And then this coefficient n, you pull it
1
in the
by n.
denominator. Yeah. Plus yes. Now all these terms are different. Here you have f of 1 by n. Here you have f of 2 by n. There's a difference here. Here you have f of k by n. So I multiply by k here and divide by k. Is that okay? Sorry. Here it will be 2.
2 and
Yeah. And in the last term it is k.
k. Yes, sir.
इक्वेशन वाली वो तो अपने सर ने करवा रखी है
And then you apply the limit.
जो सर बोलेंगे वो उसको डेराइव करनी है जो a स्क्वायर बाय गामा माइनस 1 प्लस t स्क्वायर.
Yeah. So what you will get as limit n tends to infinity, limit of each term.
f dash 1 by n.
समझ लिया.
Yes, f dash of 1 by n. So it is f dash of 1 by n. The second will be 2 times f dash of
2 by n.
2 by n plus and so on. K times f dash of k by n. And then you apply the limit. But here the extra information is given. F of x is sin x. And then we want to compute the limit of this term. So f of x is sin x. So f dash of x is what? Cos x.
Cos
So
x.
f dash of f dash of j by n will be cos of j by n.
J by n.
Okay, so this will be equal to limit n tends to infinity. Cos of 1 by n plus 2 times. Sorry, it will not come. After applying limit, we got its derivative. Cos 1 by n, 2 times cos of 2 by n, and so on, k times cos of k by n. Sorry, we need to apply limit. Yeah. No, we made a mistake. Anybody can figure out the mistake?
Sir, it's 2 f dash 1 by n plus 2 squared f dash 2 by n,
No,
like that.
no. Sorry, let me. This term, when I split the limit, this term will be equal to what? F a dash of 0.
Yes.
Yeah.
Yeah.
And
Got
this
it.
term will be 2 times f dash of 0. And so on. K times f dash of 0. So that mistake we made here. This is correct. So this will be cos 0 plus 2 times cos 0 plus cos 0 is 1. So it is 1 plus 2 plus up to k. So that is k into k plus 1 by 2. That's the answer. Is it okay?
Yes, sir.
Is it visible now again? Yeah.
Yes.
Is it followed to all of you? I hope that's fine. This is a slightly different question. Sn be a sequence of real numbers given by this 2 raised to minus raised to n, 1 minus 1 by n, sin n by. So there are basically 3 sequences. Let us separate them. First one is this. Second one is, let's call it as bn. That's 1 minus 1 by n. And third one is cn, sin n pi by. Let's write the few terms we want. So our original sequence Sn is product of these 3 sequences. And when we multiply these any sequences, we multiply them term wise. We multiply first term, first term, first term. We multiply second term, second term, second term, and so on. We go on multiplying term wise. Okay, it's not some random multiplication. Okay, so let's figure out the terms in first sequence. 2 raised to. So what is the first term of the first sequence? Is it 1 by 2? Then second term, n equal to 2, that is 2 raised to minus 1 raised to 2. So 2 raised to 1, that's 2. Second term is 2. Third term, 2 raised to minus 1 raised to 3. That's 2 raised to minus 1. That's again 1 by 2.
2 1 by 2. Yes, sir.
Yeah. So it keeps on fluctuating between these two terms. 1 by 2, 2, 1 by 2, 2, 1 by 2, 2. What about the second sequence? 1 minus 1. That's 0. First term is 0. Second term is 1 minus 1 by 2.
2.
1 by 2.
That's. And the last sequence here, sin n pi by 2. Sin pi by 2.
Oscillate. Yeah.
1 0
0.
minus 1
Then it's minus 1, then 0.
0, then
Then it will
1.
repeat.
Yes.
It will keep on repeating between these 4 terms. Yeah. 1 0 minus 1 0 1 0 minus 1 0 and so on. Okay. So let's write few terms. The product Sn. Before that, let us observe about the 3 sequences. The first sequence keeps on fluctuating, and moreover, you can observe. This is 0. Second term is half. Third term is bigger than that. Next term is bigger than that. So this is increasing kind of sequence. Is it okay? And converging to 1. Converging to.
Yes, sir.
An keeps on fluctuating between these two. Cn keeps on fluctuating between these 4. In the product, my question is, in the product, do we have 2 appearing in the product?
No, sir.
No. So what term will appear in the product? The first is 0.
First one is
Second
0, then
is
second one is also 0.
Also 0.
Third one is minus 1 by 3.
minus 1 by 2 into 1 minus 1 by 3. That's the third one. Fourth one.
Yeah. Fourth one is 0.
0.
0. So wherever there is 2 here, this 0 will ensure that that term becomes 0. Even terms of the sequence is 0. Yeah.
Yes, sir.
Even term in the product is 0. So S2n is 0 for all n. That's an observation. Okay. It's an observation. And then first is positive, third is negative, fifth is positive, seventh is negative, and so on. So S4n is positive.
Yeah.
Yeah.
Yes, sir.
And S4n minus 1 is negative.
Yeah.
Where does S4n goes? What is S4n?
Sir, S41. Sir, it is not S4n. S4n is also a 0 sequence.
Yeah, S4n is. S4n plus 1, sorry. Is it 4n plus 1?
Yes, sir.
S4n plus 1. So what is S4n plus 1?
And the next one will be S4n plus 3.
Yeah. What is S4n plus 1? So it is here you
0.
have half down because A 4n plus 1, B 4n plus 1, C 4n plus 1. Is that okay? That says 4n plus 1.
Yes, sir.
A 4n plus 1 is half. B 4n plus 1 is 1 minus 1 upon 4n plus 1. And C 4n plus 1 is 1. Yes. Yes. Where does it goes? It goes to half. Yeah. And this sequence is increasing. So this product is also increasing because this is anyway constant and this is also constant. And the remaining terms of the sequence are negative. We already observed here. So these are the only positive terms. And these positive terms increases to half. So answer to the question is we want least upper bound. So what will be the least upper bound?
Half.
Will it be half?
So,
Yeah. Yeah. Is it okay? All of you understood this?
Yes, sir.
Yes. Very good. Let's see one more nice application of Swiss theorem. Is this visible to all of you?
yes, sir.
Yeah. By n is integral 1 to 2 e raised to minus nt upon t, n greater than or equal to 1. It's a sequence. Yeah, it's a sequence because n is varying. There is n involved while defining the nth term of a sequence. So it is 1 to 2. Okay, let's observe the integrand. So the integrand. So what is integrand? E raised to minus nt upon t. Yeah. So that's nothing but 1 upon t into e raised to nt. Okay, so what can
Yes,
we
sir.
can do with this? Yeah. So anybody knows the Taylor series expansion for
1 plus x square by 2 factorial plus x cube by 3 factorial and so on.
yeah summation n from 0 to infinity x raised to n by n factorial. So that's nothing but 1 plus x square by 2 factorial plus and so on. So e raised to nt will be equal to 1 plus nt plus nt square upon 2 factorial and so on. So what is the relationship between nt and this e raised to nt? Which one is bigger and which one is smaller? That also depends on t, but here t belongs to close interval 1 comma 2. So t is positive. T is positive. Okay. So can I say e raised to nt will be bigger than or equal to nt? So with this in mind, we can say this is less than or equal to 1 upon t into nt. Yeah. Is that okay? Inequality.
Yes, sir.
Okay. So then you integrate on both sides from 1 to 2. less than or equal to, sorry, dt integral 1 to t 1 upon n square dt. So let's evaluate this. 1 upon n is common, so it will come out. We'll have 1 to 2, 1 upon t square, that is t raised to minus 2 dt. So that is 1 upon n into t raised to minus 2 plus 1 upon minus 2 plus 1, 1 to 2. That will coming out to be minus 1 by n, 1 by 2 minus 1, that is 1 by 2n. Okay, good. So we got integral 1 to, can I say this is also greater than equal to 0? Can I say the value of the integral is greater than equal to 0?
Yes, sir.
Yes, sir.
Yes. What? Yes. What will be the argument for this integral will be greater than equal to 0?
T is positive and exponential function is always positive.
Yeah. And the interval is also positive. Interval from
Yeah.
1 to 2. Lower value is at the lower limit place and the upper value is at the upper limit place. So the integrand is positive. So value of the integral is also positive. So I have the inequality 0 less than equal to yn less than equal to 1 by 2n. And 1 by 2n goes to 0. Is it okay? So by squeeze theorem, yn goes to 0. Is it okay for all of you? Possibly you may try to integrate the function. Function is integrable, no doubt. But getting a answer may not be possible. You may not able to integrate the function. Function is integrable because it is continuous on a closed and bounded interval. So it is integrable. There is no doubt. But computing its integral may not be easy. So we are bypassing that. We are using power series expansion for e raised to x. One needs to be careful. This power series expansion is valid for which values of x? So for e raised to x, it is valid for all x. So I don't have to worry what value I will substitute in place of x. Doesn't matter. It is true for all values of x. So, and then simple application of squeeze theorem will give me the required answer. Now let us have one again different variety of problem. Let an be a sequence defined as follows. A1 is 1, an plus 1 is 7, an plus 11 by 21. Which of the following statement is true? An is an increasing sequence which diverges. An is an increasing sequence and the limit is 11 by 14. An is a decreasing sequence which diverges. So decreasing sequence converges to 11 by 14. So two of the options speaks about convergence of that sequence. Two of the option speaks about convergence of a sequence. So is it possible to compute the limit? So what formula does an satisfies? An plus 1 is equal to 7, an plus 11 by 21. Let us apply the straightforward limit without worrying about whether limit exists or not. Let us try applying the limit n tends to infinity on both sides. An plus 1 is equal to 7. Limit n tends to infinity, 7 an plus 11 by 21. So if you assume that an goes to L, then you'll have L on the left hand side And here we'll have 7L plus 11 by 21. Let us simplify. 21L minus 7L is equal to 11. So from this, I'll get L is equal to 11 by 14. 11 by 14. This is that magic figure which is appearing in the option. Is that okay? 11 by 14. So if at all sequence AN is convergent, it will converge to 11 by 14. If at all sequence AN is convergent, with this assumption, AN will converge to 11 by 14. But then how do we guarantee AN is a convergent sequence? Or AN may not converge. So it is, if I define a function by using this expression, what is that? AN plus 1 is equal to 7 times AN plus 11 by 21. So I am defining a function by using this expression. Of x is equal to 7x plus 11 by 21. And then we observe that A1 is 1 and A2 is f of 1. A3. What is A3? A3 is f of A2. That's nothing but f of 1. Is it okay? A4, f of A3. That's nothing but f of A2. That's nothing but f of A1. So you go on repeatedly applying f. You are generating terms of the sequence. So this suggests something which we have already studied, fixed point iterations. Fixed point iterations. So geometrically, it's very nice concept. X-axis, y-axis. There is y equal to 7x plus 11 by 21. This means 21y equal to 7x plus 11. So that means 7x minus 21y equal to 11. That's a straight line. This is the equation of straight line. So can you plot the straight line? X equal to 0 is 11 by 21, somewhere here. So what are the points? And if I put y equal to 0, what I'm going to get? X ka value minus 11 by 7. Is it okay? I'm just plotting the straight line equation. Minus 11 by 7.
सर x की वैल्यू 11/7 ही आएगा पॉजिटिव में, y की वैल्यू आएगी नेगेटिव.
Y equal to this. You substitute x is 0, 11 by 21. Y is 11 by 21. Is it not correct? X का वैल्यू 0 रखा, y का वैल्यू 11 by 21. And y का वैल्यू 0, we'll have x is minus 11 by 17. Yeah, we
तो
have
जब
written this
x
equation
0
wrongly.
होगा तो
Sir, 7x minus 21y minus 11.
Yes, 7x minus 21y is equal to minus 11. We have made a mistake here. Okay.
Yes sir, then it is
Correct.
correct.
Yeah. So here you'll have minus 7 minus 11 by 7 comma 0. So you'll have a line like this. Yeah. This is y equal to 7x plus 11 by 20. And how does y equal to x will look like in this diagram? It be like this. This is y equal to x. What is the point of intersection? These two lines, they're intersecting at a point. At this point of intersection, you'll have point of intersection. We have, what do we have? F of x equal to x. That's a fixed point because the line, another line that we have plotted is nothing but y equal to x. So these two y value will match. That means 7x plus 11 by 21 is equal to x. That means f of x is equal to x. That's a fixed point of f. Is it okay?
Yes, sir.
Point of f. Yeah. So, and that we already computed. Or you can-
11 by 14.
yeah. X is equal to 11 by 14. So this 11 by 14 comma 11 by 14. Okay. And now we are starting with iteration. First value a1 is 1. So this is 11 by 14. So a1 is 1 will be on this side. a1 is 1. So you have to go till the graph. This is the graph of that function f. From there you have to go on the line y equal to x. So this is my f of 1. Okay. The point at which intersect the line y equal to x, from there you have to go towards f of x vertically. When you are going towards the function f of x, you have to go vertically. And when you are going towards the line y equal to x, you have to go horizontally. And then you have to go towards y equal to x. This is a2. This is f of a2. Then from intersection, you have to go like this, go like this. You'll have f of a3. So from the diagram, if we zoom like this, it will go like this. First horizontal, then down, then horizontal, then down, then horizontal, then down, then up. And it will approach towards 11 by 14. From the diagram, it is clear. It will approach towards 11 by 14. And you'll have all terms of the sequence appearing on the y-axis. From this is obvious, f of a1 is the highest value. F of a2 is smaller than f of a1. F of a3 is smaller than f of a2. So f of an is a decreasing sequence and converges to 11 by 14. Is it okay? Decreasing sequence and decreases to 11 by 14. So though we haven't actually played with terms of the sequence, we have figured out some function from the nth term of a sequence, and we have used smartly fixed point iteration method to get the information about the sequence. That sequence actually decreases and decreases to fixed point 11 by 14. Is it okay?
Yes, sir.
Yes, sir.
Can try a few problems. I will just paste it here. You can try them. One more. So last 15 minutes are remaining. So let me revise or let me recap infinite series. We have already studied this in second year, possibly if you are a student of Mumbai University. So for a given sequence an, a1, a2, and so on, if you compute addition of all terms, a1 plus a2 plus a3, that means we are considering addition of all terms of the given sequence. Okay. We already know that addition of finitely many real numbers is always finite. But what happens if you go on adding infinitely many real numbers? It seems that when you add infinitely many real numbers, we may get some infinity as answer, but that's not the case. Sometimes we do get finite number as an answer. So we are interested in studying all those sequences for which if I add all terms of that sequence, I get some finite number as answer. So how do I talk about infinite addition? So rather than talking about infinite addition, for a given sequence, we consider Sn, a1 plus a2 plus up to an. For a given sequence, we consider n for all n in n. That's called as sequence of partial sums. So from given sequence, we have computed another sequence, Sn, and we already have knowledge of what do we mean by a sequence is convergent, and we have studied several results about convergence of a sequence. So we can ask whether the sequence Sn converges. So if Sn converges, we say infinite series summation an converges. And if, or rather, moreover, what is the sum? Sum is limit of Sn. Sum is limit of Sn. So we are interested in computing all such kind of infinite sums, in which case we get some finite number as a answer. Okay. We have studied several results related to infinite series and so on. Let me recall a few of them. The first result that one cannot forget is necessary criteria. What does this say? If summation an converges, then an goes to 0. Nth term of that sequence from which you have constructed the series, that sequence is a convergent sequence and it converges to 0. So this necessary criteria, most of the time it is used in contrapositive sense. So what is contrapositive of this? If an does not tends to 0, then summation an diverges. Okay? So if nth term of a sequence is not going towards 0, it may be convergent, but not converging to 0. It may be converging to some positive real number or converging to some negative real number, or maybe not convergent itself. Then the series diverges. Then we have seen some telescoping kind of series, like for example, summation 1 by n into n plus 1. We can actually compute this infinite sum. Then we have seen something called as geometric series. Then we have seen a very special kind of series, that is harmonic series, summation 1 by n, and we know that it diverges. Harmonic series diverges. Reciprocal of all addition of reciprocal of all natural numbers. This diverges. Yeah, Arpita, you can ask.
Sir, why it is necessary to converge an to the zero rather than any finite number?
Yeah, because Sn is defined like this. You followed the definition of Sn. A1 plus A2 plus and so on,
Yes,
An. So what is Sn minus 1?
it will be a1 plus a2 up to an minus 1.
So what is Sn minus 1?
It will be only an.
It will be An. Then
Yeah,
limit of, you take limit on both sides.
yeah.
Limit n tends to infinity of An, that's equal to limit n tends to infinity of Sn.
Okay.
Yeah. Okay.
Thank you, sir. Got it.
Yeah. So this limit and this limit is same. So An has to converge to 0. Yeah. Let us continue. Then we have seen something called as alternating series. Summation minus 1 raised to n times An, where An are positive terms, strictly positive terms. Ans are strictly positive. If I expand this, is A1 minus A2 plus A3 minus A4. Terms are strictly positive, but signs of the terms are alternating. First term is positive, second term is negative, positive, negative, and so on. Such kind of series is called as alternating series. And we do apply Leibniz test for checking convergence of such kind of series. So it has some hypothesis. What is the hypothesis? An is greater than 0. Second, it is decreasing. Third, it should go to 0. Then summation minus 1 raised to n plus 1 An converges. Okay, that's a Leibniz test. And then we have studied several tests for convergence of series of non-negative terms. The first is like comparison tests. Second, limit form of comparison test. Third, ratio test. Fourth, root test. Then we have also studied possibly fifth one, Cauchy condensation test. And then we are also aware about P-series test. Summation 1 upon n raised to p. This kind of series are called as P-series and is convergent if p is greater than 1. P is greater than 1, this series converges. Okay. These are all the several tests we have learned for checking convergence, divergence of infinite series. One thing you can note here is that only in these two cases we may be able to compute actual sum of your infinite series. For rest of the cases, all these tests like Leibniz test, comparison test, limit form of comparison test, ratio test, root test, all this, any other test that you have learned for checking convergence and divergence, you can only check whether your series converges or diverges. If you want to find its sum, then you need to use some higher mathematics. With these are only tests for checking convergence and divergence. They do not tell you anything about what is that infinite sum and so on. Yes, it will say only about whether the given series is convergent or divergent, but it will not give you if that series converges, then where will it converges and so on. Nothing like that. Only in the case of telescoping series or geometric series. Geometric series के लिए कौन सा टेस्ट है? Geometric series test. Where does it converges? A upon 1 minus r. If your r is less than, absolute value of r is less than 1. ठीक है. And telescoping series, we actually compute the sequence of partial sum. It is possible to compute sequence of partial sum actually, and we can actually compute limit of that sequence of partial sum. So here we apply the definition of convergence of series to find its sum. Okay, so except from these two, if you choose any other test, those are only will tell you whether your series converges or diverges. Apart from this, we have also learned something called as power series. Expression of the type n runs from 0 to infinity, or sometimes it may start from 1 to infinity. Such kind of expression is called as. So if you take a power series, it is always convergent at x equal to a naught. So we are assuming 0 raised to 0 is equal to 1. That's a slight assumption that we make when we study power series. Okay. So we are interested in calculating what values of x in R the series converges. The series converges. If I fix value of x, is it visible to all of you? Yeah. So we are interested in calculating values of x for which the given power series converges, and there are some results which says that if your power series converges, suppose there's a center point, if it converges for this x, then it will converge around an interval of length x mod x from that center. So I'll have the maximum possible interval centered, and you'll have something called as radius of convergence for a given power series. So there are formulas by using ratio test and root test for computing radius of convergence of a power series. Okay, so I suggest you revise all this infinite series. Also something called the radius of convergence and interval of convergence of power series. Okay. Next time we will see problems based on infinite series and power series. Is it okay for all of you?
Yes, sir.
We will stop for today.
Sir, could you
Yes.
explain the sign pi by 2 plus 5 pi by 2 k by n question using Riemann integration again?
Yes. Is my screen still visible? Yeah. Where it is?
Yes.
Yeah. This we consider this function f of x is equal to sine pi by 2 plus 5 pi by 2 x. Okay, because we have observed k by n in the limit here. So we are replacing this k by n by x. Okay. So we are considering this function f of x is equal to sine pi by 2 plus 5 pi by 2 times x, and we are considering the interval 0 comma 1. But instead of taking upper Riemann sum or lower Riemann sum, we are taking special kind of Riemann sum that is formed by using stacked partition. So what is stacked partition? We are considering this partition. At the same time, from each subinterval, we are choosing a specific point k by n belonging to kth subinterval, and that point we are calling it as xk star. Okay. And then we are considering Riemann sum with respect to the stack partition. So that Riemann sum will be like this. Limit n tends to infinity. Sorry, Riemann sum is like this. Summation k from 1 to n f of xk star, f evaluated at this xk star, that is it, into length of the ith subinterval, that is 1 by n. Okay. But what is f of xk star? F of x is this. Sorry, here. F of x is this. So f of xk star. So you replace x by xk star. What is xk star? K by n. Replace x by k by n in this. So we get something like this. Is it okay up to here?
Yes, sir.
Yeah. And then you multiply by length of the interval, and then you sum it over from k from 1 to n. And then you
Yes,
take
sir.
limit.
Okay.
So this will be equal to integral 0 to 1 fx dx. Let's compute what is integral 0 to 1 fx dx. That's nothing but sine of pi by 2 plus pi by 2 times x dx. What is the integral of sine? Minus cos pi by 2 plus pi by 2 x divided by coefficient of x, pi by 2 x, and then you integrate from 0 to 1. So what you
Yes,
are
sir.
going to
Okay,
get?
got it. Yeah, got it.
Is it okay? Can you complete now?
Yes, sir.
Yeah.
I can do it. Yeah. I was just confused about the first one.
Yeah, okay. But only one more thing you have to take care is that we haven't considered this pi. Okay. So whatever answer you will get, you have to multiply by pi to get the final answer, because in the sum itself we have pi by n. Okay. So
Yes,
pi
sir.
and this pi will get cancelled. We have answer 2 by 5. Yeah. Okay.
Yes, sir. Thank you.
Okay. Thank you. We'll stop for today.
Participants, if you have any other questions, you may please ask. I hope there are no questions. Thank you so much, Deepak sir. And I would like to mention that there is a change in tomorrow's timing. So tomorrow you'll be starting your session at 5:30. So we'll have tomorrow's session from 5:30 to 7:30 by Dr. Anand Chitra. Okay, so participants, please note the change in time. Thank you.